So I thought for the first time when we introduce each other to each other, and I introduce you, the brain, I want to introduce you what I see today, and this is a choice, 5 very exciting things that are happening today in terms of science of the brain. This will be the Connectomics, which is a buzzword that you should know, the Brainbow technology, which is a beautiful new technology. I want to talk a little bit about the interface between brain and machines. I want to discuss a beautiful technology, the optogenetics, and eventually I want to show you just a glimpse, just a teaser for the Blue Brain project in terms of simulating the brain mathematically, building models for the brains in the computers. So I want to just highlight 5 of the recent excitements in brain research. So we start with modern neuroanatomy. We need to have the wiring diagram. We need to have the roadmap or the blueprint of the brain. And this is, of course, something very fundamental that actually started many, many years ago, not so many, 120 years ago. And this is what I see as the beginning of modern neuroscience. So when I say the beginning of modern neuroscience in a systematic way, in a scientific sense, I'm talking about these 2 characters. Camillo Golgi, the Italian, Ramon y Cajal, Santiago Ramon y Cajal, the Spaniard, both great anatomists, really are giants. They are working very systematically to develop methods, both optical methods, so microscopes, but also staining methods to be able to look at the brain, to stain the brain, and to see what are the elements that build the brain. And so these are drawings, 120 years old drawings, in this case from Ramon y Cajal in Spain. And you can see that after using the technology that was developed by Golgi, pouring, so to speak, into pieces of brain, dead tissue, a particular dye, the Golgi stain, the Golgi dye, you can suddenly see this kind of elements popping up. So some kind of elements, now we call them neurons, but then they did not call them neuron. They saw some kind of things that look like cells in the brain. This is the first systematic study by Ramon y Cajal about the different parts of the brain in terms of the elements, the anatomy, the building blocks, the units that build this system. Lucky for them, the Golgi stain, the Golgi staining method, was very, very sparse. So it didn't stain everything, because if you would stain the brain and everything would be colored, it would become completely dark, black. Because it's so packed, it's so dense, this jungle of nerve cells are so packed that if everything would have been stained, you could not see individual elements. It would look dark. So about less than 1% or 1% of the cells, for some unknown reason, pick up the dye, and then you see these beautiful structures. They got the Nobel Prize in 1906, but they did not agree with each other at all. They actually did not agree with each other on the most fundamental thing. So Golgi thought that it cannot be that the brain, unlike other regions, are built from individual cells. This did not fit his view about this beauty of the brain. You could not think that the brain, like any other system, is built from one cell and another cell and another cell individually. Ramon y Cajal thought, no, these are like any other living tissue, are built from units. So here are the units, he says. But they don't really know if they are connected physically to each other or not at this resolution. You don't know if this element and these elements are not really physically a continuum or not. So they fought. It was a big fight. It was a very big fight. And we know today that Ramon y Cajal was right. These units typically do not touch each other. They are separate elements. There is a gap between them. These elements, we later call them neurons. And so this is a later term, not by them. But today we do new kind of anatomy, and you should see that this old type of anatomy, which was the foundation of understanding the circuit at different regions in the brain, we are now doing modern anatomy, which is called the Connectomics. So here is Connectomics. The idea of Connectomics is to cut very, very, very thin slices of the brain. Slice after slice after slice, very, very thin, at the nanometer scale. So nanometer is 10 to the power of minus. It's a thousandth of million of a meter. Very, very thin slices. You detect the structure within each slice separately, and then you put the slices back, so to speak. You align them back one on top of the other, one after the other, after the other, after the other, at a very fine resolution, and then you can reconstruct a piece of a brain. A very small piece of a brain in this case, but then you can really, really see whether they touch each other or not touch each other. This is the electron microscope system. And eventually you can see that cell number 2 is making contact, synaptic contact. We'll talk about this, and which part of the brain is touching of the cell touching another part of the cell. So you really start to develop a very systematic method to really map the whole brain in 3D. This is the connectomics. It's a big endeavor. We did not yet succeed to reconstruct a whole brain, but we did succeed to reconstruct pieces of brain and really, really learn and study who are the elements that build the brain, who is connected to who, and who is not connected to who. So we start to get a roadmap at the level of cells and synapses, the connection between the cells. This is a big, big endeavor. It is done at several central locations in the world, very expensive one, to have this huge microscope and to cut, and reconstruct. But we are getting, for the first time ever, the full 3D anatomy of a whole brain tissue, the connectomics. Let's look at it. How does it look when you reconstruct it? And in this case, I'm going to show you a piece of the cortex of a mammalian, of a mouse, that is reconstructed in the way that I showed you. This is done in MIT. So you see piece by piece by piece by piece. You put them together, as I explained before. You, of course, artificially dye the cells, because the cells in the brain are not blue or purple. But you artificially, while you reconstruct, you dye the separate cells, and suddenly you see the network. This is the network in your brain, in this case of a smaller mammal, but it looks very similar. And you see all these wires that we'll talk a lot about them. We'll talk about axons, and we'll talk about dendrites, and we'll talk about the connection between them. But just to see, to show you the jungle within your brain. This is what we have, and this is the anatomical foundation, on top of which you can see also blood vessels going through. So you see really a very small piece of your cortex, the mammalian cortex, and that's what we need to understand. So we are going to go into the details, but we completed understanding what is the connectomic project for now. Why is it so important? Why is it so important to understand, to get the details of the brain structure? What is the prospect? What is the future of this connectomics endeavor? Where are we heading? So just to give you a few points, some prospects about connectomics. As I said before, we will, for the first time, we will have a complete, full, what we call blueprint, wiring diagram of a network. So if I want to understand the city, if I want to understand the globe, I need to know where are things and who is connected to who. So this is the roadmap of a circuit, and this is very fundamental. When I say I understand the circuit, I really need to know how it is structured. So that's very fundamental, very basic. But the main thing is that because we have a particular structure which is not random and it has a particular principles underlying it, we will be able eventually, and that's the hope, to connect how this structure subserve a particular function. How a structure of my retina in the eye subserve my capability to see, or at least to start to see. So the connection between the structure and the function, which is actually will be specifically highlighted in lecture number 6, is what we need to do. You have a structure, you have a function, I move my hand, and I want to understand how this particular structure that controls my hand is operating. So I need to know the structure, but on top of the structure, I need to know something about the activity that gives rise to behavior. So this connection between structure to function is the most fundamental thing. And finally, when one gets sick, let's say with Alzheimer's or Parkinson, something about the structure, not only, but something about the structure, but also something about the activity, both may go wrong. So if something with the structure goes wrong, I may become autistic, I may become schizophrenic, or I may become a genius. So we want to connect the structure to the function. This will be the focus of lecture number 7.